Now that we've seen the greenhouse effect, we can start to look at the temperature structure of a planet's atmosphere. By temperature structure, we mean the way temperature changes with altitude. As we said earlier, the temperature structure is much more complex than the pressure structure. That's because there are several different ways that an atmosphere can be heated up. We've already seen one of these, the greenhouse effect, but there are others we'll have to consider as well. The main layers of the atmosphere, from top to bottom, are the exosphere and thermosphere, the stratosphere, and the troposphere. Not all worlds have all of these layers. In fact, only a few have a stratosphere. Also, you'll often see that the stratosphere is divided into two regions, the stratosphere and the mesosphere. However, since there's just one heat source for both of these, we'll lump them together here. We'll start with the part of the atmosphere we're most familiar with, the troposphere. This is the lowest layer for any world that has a substantial atmosphere. It's defined as the part of the atmosphere near the ground that gets cooler as you go upward. The diagram on the right shows the temperature structure for the planet Venus. The graph shows temperature across the bottom and altitude along the side. The bottom half of the diagram, everything below about 100 kilometers, is troposphere. As you can see on Venus, the surface temperature is very high, around 500 Celsius or over 700 Kelvin. But as you move upward, the temperature drops off until it's around minus 100 Celsius or less than 200 Kelvin at the top of the troposphere. We've already talked about what causes a planet to have a troposphere, the greenhouse effect. The ground absorbs sunlight and then radiates this as infrared light. This light is trapped in the lower atmosphere by greenhouse gases, which keep the surface hot. In effect, the troposphere is being heated from below. The troposphere is also the part of the atmosphere with the highest density and pressure. On any planet that has a troposphere, it makes up more than 90% of all the air. This means that changes that happen in layers above it usually have very little effect on the troposphere. Another feature of the troposphere is strong convection. When you heat a fluid like air from below, the warm air tends to rise and the cooler air sinks. This convective flow causes a lot of mixing of air from different altitudes. It also plays a big role in weather, as we'll see shortly. Here on Earth, one way we experience this convective motion is when we fly in an airplane. When the plane is close to the ground, the flight often seems very bumpy because the plane is moving through upward and downward moving air in convection cells. However, when the plane gets up several kilometers, it's above most of the convection, so the flight usually becomes much smoother. Now we'll move to the upper part of the atmosphere, defined by the exosphere and thermosphere. On this same diagram of Venus temperature structure, this is the upper half of the graph. The temperature trend here is opposite what we saw in the troposphere. The thermosphere starts out coldest at its base and gets hotter the higher up we go. However, remember that the density of the air is dropping as we move upward. So when we say that the thermosphere is hundreds of Kelvin, we really mean that the gas molecules are moving quickly. Since the density is very low, you wouldn't feel very hot if you were in the upper thermosphere. There aren't enough molecules to transfer much heat to your body. The energy that warms up the thermosphere and exosphere comes from X-rays emitted by the sun. While most of the sun's light is visible, a tiny portion comes in the form of X-rays. These high-energy photons are absorbed by the first atoms and molecules they hit when they reach the atmosphere, which is why all of the heating they cause happens at high altitude rather than in the denser gas closer to the ground. Another thing we see in the thermosphere of some worlds is auroras. High-energy particles from the sun crash into the upper atmosphere and make it glow. These are often directed by the planet's magnetic fields towards the poles. This image shows some auroras as seen from Earth orbit. As we said earlier, there isn't really a clearly defined upper end of the atmosphere. Instead, the gas just keeps getting thinner until it merges with the interplanetary medium. If you get high enough up in the atmosphere, you find that the atoms and molecules rarely, if ever, collide with each other. Instead, they travel long distances like little projectiles around the planet. This is the region we call the exosphere. When we look at escape of atmospheres later on, we'll see that this is the region gas molecules can escape into space from. Smaller worlds in our solar system, like the Earth's moon, are often considered airless. In fact, they usually do have a small amount of gas surrounding them. However, this gas is so thin that it behaves as simply an exosphere. Many planets with atmospheres, such as Venus or Mars, only have the layers we've just described, the troposphere, thermosphere, and exosphere. However, a few, like the Earth, have a warm middle layer we call the stratosphere. The stratosphere gets warm because it's where ultraviolet light is absorbed. This means that there has to be a gas in the atmosphere that's a good UV absorber. In the case of the Earth, that UV absorber is ozone, which is made of 3 oxygen atoms bound together. This is different from the oxygen gas we breathe, which is made from 2 oxygen atoms bound together. Ozone is very unstable. It likes to react with other molecules. So to have much ozone, there has to be a lot more ordinary oxygen gas around. That's why the Earth has an ozone layer, while Mars and Venus don't. Their atmospheres are dominated by carbon dioxide, and they've got very little free oxygen, so there's even less ozone. Since ozone is a great ultraviolet absorber, it creates the warm layer we call the stratosphere. It also means that very little of the sun's ultraviolet light makes it to the ground. Remember that ultraviolet photons have enough energy to damage organic tissues, causing sunburns and skin cancers in humans and other animals. So the fact that UV is blocked makes the Earth's surface much friendlier for life. In fact, the geologic evidence suggests that life on Earth didn't leave the oceans and colonize the land until there was enough oxygen in the atmosphere to create an ozone layer, making the surface habitable. Lastly, don't confuse the ozone layer with the greenhouse effect. They are very different processes happening in different parts of the atmosphere and caused by different gases. The only thing they have in common is that humans have had an impact on both.
Here is another table to fill in. This time, it looks at the different layers in a planet's atmosphere. In this case, you should also create your own graph of the temperature structure for the Earth. Remember, this is a graph showing the temperature at different heights in the atmosphere. Make sure you label the axes and the different layers in the atmosphere. Normally, you can't actually see the different layers in a planet's atmosphere. But this image taken by the Space Shuttle crew does show us these layers in the Earth's atmosphere. The troposphere is the densest layer of the atmosphere, so it's the part that is scattering most of the sunlight towards us. The sun is just below the horizon, so the only way we can see its light is by scattering. You can also see a lot of clouds in this layer. Just above it is the stratosphere, and above is the gradually thinning gas of the thermosphere and exosphere. Notice that it's hard to see a clear edge to the upper atmosphere. It simply fades smoothly into space.
Now you can apply your understanding of what causes the different temperature structures to see if you can predict what would happen if we changed the sun's light. Treat each of these as a separate case. Don't try to combine them into just one. For each one, draw the temperature structure graph and describe how and why it's different from the current structure for the Earth.
Here's a making sense table we've seen before. The one where you describe the 4 major ways light and matter interact. Now that we've looked at planetary surfaces and atmospheres, it's time to add in some astronomical examples based on the things you've learned in the last few chapters.